All right, everybody. So this lesson is still nuclear chemistry. We're going to study something called half-life today. You will need a calculator, and you will need a reference table. Specifically, we're going to use table T, and then your calculator. If you have a scientific calculator, that's best because it will have some fraction settings, and we're going to be doing some fractions in this lesson. There is a bookwork that's associated with this lesson. We'll do it in class tomorrow after you ask me whatever questions you have. And it's basically just to answer questions 34 to 47. And yeah, it'll be due tomorrow. So aim today, what is half-life? Please copy down these questions for the do now and have them ready for class tomorrow. Just make sure it's on a separate paper and file it under classwork in your binder, and then the notes for this lecture, have them under notes. So half-life. We've been learning that nuclei can be unstable, and when they're unstable, they break down and they throw little particles that were once inside the nucleus out. When that happens, we refer to the entire process as decay. So the rate of decay is measured with this idea called half-life. And the way we do it is we just look at a whole bunch of atoms. We'll call it a sample from here on out. So we look at a sample of atoms and we measure how many of them decay in a given unit of time. So you can't really know, as an individual, if an individual atom will decay, but you can look at the entire sample and determine the rate of decay sort of in general for an average atom. So what I just plugged in here was, I said law of averages, because the law of averages basically says that although you can't say a lot about an individual, that you can refer to an average rate if the number of particles is large enough. All right, so in terms of this actual rate, it is going to bring up a new vocabulary word, and it's called half-life. And half-life has a definition, which is the time taken for half the atoms in a given sample to decay. Obviously, record that in your Cornell notes. But half-life is actually a unit of time. So I know that the definition was a whole sentence here, but it's really just going to be some unit of time, such as seconds or days or years or hours. And in that unit of time, half of the atoms are decaying. So that part's always true, that whenever a half-life has passed, that half of the atoms have decayed. But the thing that will differ from element to element is how long that takes, which is why the half-life is really a unit of time. So a note that I should say before we go any further, though, is that this idea of nuclear decay is completely random, and it does not depend on any outside factors. And two of the ones that the Regents will bring up from time to time, and just it's almost like a true or false scenario. They'll just be like, does temperature affect half-life? Does pressure affect half-life? Those are two common ones they'll ask about. And the answer to both of them is no. Nothing will affect half-life except for the identity of the element itself. So every element has its own half-life and nothing will change it. So in your very first baby introduction to half-life, I think that you should check out this particular graph, which I think is a really great intro to half-life. On the x-axis, it is saying that we're dealing with a particular isotope of oxygen-15. And it looks like it's giving us the sample size in milligrams, which is a unit for mass. And it looks like at the very beginning of the experiment, you have 20 milligrams of oxygen-15. And so it starts out with 20 milligrams. It goes from 0 all the way up to 20. But it looks like some time period later, that number of milligrams is decreasing. And at this second purple bar, I only see 10 milligrams of oxygen-15 remaining. So what I would like to point out is that if you started with 20 milligrams and after this first little time period you have 10 milligrams, then that also means, just by definition, that we have made it through one half-life. So as a review, it says half-life is the time taken for half the atoms to decay. So 20 milligrams to 10 milligrams, you only have half of the atoms, and that by definition is a half-life. So I've labeled that down here as your first half-life. Now this process will repeat, and the rate of that decay will stay the same. So basically, if the first half-life is this much, then the second half-life will be an equal amount of time, and the third half-life would be an equal amount of time, and so on and so forth. They just add on to each other. So I'm just going to go through the second half-life to make sure that you've got it, but we started at 20, one half-life later, we have 10 milligrams. Another half-life later, after our second half-life, we have only 5 milligrams, so 10 divided by 2 is 5. And another half-life later, after the third half-life, we will have only 2.5 milligrams remaining, because 5 divided by 2 is going to be 2.5. This process can repeat and repeat and repeat until you have almost no milligrams left, and then eventually you would have no milligrams left. So it can decay all the way. Okay, so let's answer our first question about half-life. It reads, what is the half-life of oxygen-15? Remember, when you give an answer for half-life, it needs to be a unit of time. So half-life is always measured as a unit of time. So when I ask you this question, what is the half-life? You have to say some kind of time unit, like seconds or days or hours. The easiest way to do this one is just to check out the graph. So oxygen-15, it looks like, for instance, it starts at 20 milligrams, and then some time period later it has 10. That time period that it took to go from 20 to 10, that is the half-life. So the time period to go from 20 to 10 looks like it was 2 minutes long, because I went from 0 minutes to 2 minutes. So that's my answer. All right, so my second question is, how many half-lives have passed when 25% of the sample remains? So in this question, I didn't say what is the half-life, I said how many half-lives. So your answer is just going to be a number like 1 or 2 or 3. All right, so when 25% of the sample remains, you need to think about how much there was at the beginning, which of course was 20 milligrams. 25% is about a fourth of that. So a fourth of 20 would be 5 milligrams. That is this one. So when it says how many half-lives have passed when 25% remains, I'm just translating that into the graph. It's saying how many half-lives have passed when you go from here to here. And you can see that that was 2 minutes, and then 4 minutes, or 1 half-life, 2 half-lives. So to show my work, I just said that 20 divided by 4 is 5 milligrams. That's how I found the 25% guy. So 25% is 5 milligrams, that is here. And then it looks like it took 2 half-lives to get there. All right, so I have an example of how to do a half-life math question for you guys. But before we do that, you can just take a look at this little table. This used to be on the reference table up until 2011, I believe. So for the last 4 years or so, it's not been on the reference table, which means that the regents don't expect you to use any of these equations. But some of them are helpful, and if you have a question about how to use one, please see me after class. It's just that you won't be given them on the reference table, but you can have them for now. All right, so here's my question. Where can you find the half-lives of many common radioisotopes? And it's on your reference table, and it is called Table N. It has a lot of other information on it as well, but it does have half-lives, which is an important thing you need. Second question. Chromium-51 is an unstable isotope with a half-life of 28 days. So if I'm giving you the half-life, the assumption is that it's not on table N. But so chromium-51 is 28 days half-life, and the sub-question is, what fraction of a sample of chromium-51 will remain after 168 days. So I'm going to show you the way I would suggest working through these, but I will admit right now that there are many ways to do this correctly. But the first thing I would say to look at is that it's been decaying for a total of 168 days, and every 28 days, the ratio of stable to unstable nuclei decreases by half. So basically 28 days is like the time period, but that's going to happen several times over the course of 168 days. So the first thing I'm going to do is divide those two numbers. And 168 over 28, I'll calculate that and come right back. All right, so 168 over 28 is 6. So that means that 6 half-lives have passed during the course of this decay. And it's not really quite the answer to the question, because the question actually says what fraction of chromium-51 remains. This is an important part of finding out the answer. Basically, 6 half-lives have occurred, so I'm going to label that down here. This is just one way to solve it. So 6 half-lives have occurred, and after every half-life, you should only have 1/2 of the amount that there was before that half-life. So after one half-life, you have 1/2 remaining. And after the second half-life, you should have 1/4 remaining. And just in case you're wondering, the way I got that was I multiplied 1/2 by 1/2, and that gave me 1/4. After 3 half-lives, you should expect 1/8 to remain, which, following from the previous example, is just going to be 1/2 times 1/2 times 1/2 would give you 1/8. After 4 half-lives, I'm expecting 1/16. After 5 half-lives, I would expect 1/32. And after 6 half-lives, I will expect 1/64 of the original amount to remain. And this is my final answer, 1/64. So my next example says, if a sample of chromium-51 has an original mass of 52 grams, what mass will remain after 168 days? So a lot of this question is the same as the one before. It says 168 days, it's still chromium-51, so the half-life will still be 28 days. So all that's still the same. And I also know that after 168 days, I will have 1/64 remaining. So I'm going to go ahead and start with that piece of information. 1/64 remains. But the question reads that there was an original mass of 52 grams, and what mass will remain. So they're not asking me for a fraction, which means that I can't have my answer end up as 1/64. But one easy way to solve it would just be to take that fraction, 1/64, and multiply it by the original mass, which in the question is stated as 52. So in other words, 1/64 of 52 grams will remain. I'm going to calculate that, and I'll come right back. So I just ran through an example, but I got 0.8125 grams. And then after I was finished doing that with the calculator, I noticed that my original plan was for you to use your brain to solve this one. So I'd actually like to show you an example of how to do that. I'm going to zoom in a bit so I can get a bit more space. And it's the same idea. We have 52 grams to start, and we're going to go through 6 half-lives. And I'm just pulling that back from our previous example. So 6 half-lives on an original 52. Check out this other method that would help you avoid using a calculator. So we start with 52. That's going to be at half-life 0, meaning like that's the original time, I guess. After 1 half-life, you should expect 26 grams. After 2 half-lives, you would expect 13 grams. After 3 half-lives, this is going to get tricky for me. I would expect 6.5 grams. After 4 half-lives, expect 3.25 grams. After 5 half-lives, expect 1.625 grams. And after 6 half-lives, expect 0.8125 grams, which shouldn't surprise you very much. that is the same answer that we got by doing that same calculation but with a calculator. So 2 different methods for getting the same answer. All right, so next slide. So we have some practice questions here. This slide and the next slide both have these practice questions. So what I'm going to do is I'm going to go through all 4 of these questions with you. And then the ones on the next slide you can copy down on a separate piece of paper, and it can become a pair up for tomorrow. All right, so I'll zoom in. Remember, use table N and T to help you solve all of these questions. All right, number 1. Which of the following 10-gram samples of a radioisotope will decay to the greatest extent in 28 days? So greatest extent is actually the key word here. And I want to point out that it would be really easy to think of maybe the 10 grams or maybe the 28 days as being the key to the question. But since each one of the samples is starting at 10 grams, and each one of the samples is decaying for 28 days, then you can actually ignore both of those numbers, since they're going to be applying to all of the samples in all the choices. So that means that the only thing that really matters for this question is greatest extent. So, which one would decay to the greatest extent? That's going to be the one that decays the fastest, right? So the one that decays the fastest would be marked by the shortest half-life. Because if you have a short half-life, that means that it doesn't take very long for you to decay. So what I would suggest is pausing the video here, getting out table N, and looking to see which one of these isotopes has the shortest half-life. Okay, so I just harvested some data from table N, and what I found was that this guy, francium-220, has the shortest half-life because it has only 27.4 seconds before half of the sample decays. It looks like the next best answer would be iodine-131, but it takes more than 8 days for half of a sample of it to decay. Next question. How many hours are required for potassium-42 to undergo 3 half-life periods? All right, so you're sort of up the proverbial creek without a paddle on this one unless you have table N. Table N's a wonderful help because it's going to give me the half-life information that I need for potassium-42. Just looking at the table, I see that the half-life for potassium-42 is 12.36 hours, which means that every 12.36 hours, half of the sample of potassium-42 would decay. And in this particular question, it says that 3 half-lives have passed, which means that it has not just been one 12.36 hour period, it's been 3 of those. So I'm going to multiply that by 3, 12.36 hours times 3. Okay, so I got 37.08 hours. That's the amount of time it would take to go through one half-life, to go through 3 half-lives. And just scanning the question, how many hours? Yes, that's my final answer. That's how many hours it would take for potassium-42 to undergo 3 half-lives. Next question. A radioactive element has a half-life of 2 days. Which fraction represents the amount of an original sample of this element remaining after 6 days? All right, so 6 days of time, but the half-life is 2 days. So if it's been decaying for 6 days, and every 2 days it decays by half, then that means that we've been through 3 half-life periods. 3 half-lives have passed. And they want to know a fraction that remains. So after the first half-life, obviously, you have a half remaining. And after the second half-life, there should be a fourth remaining. And after the third half-life, expect an eighth to remain. So it's been 3 half-lives, and that means that an eighth of the sample remains. Okay? If 1/8, all right, so I'll go ahead and write that in. If 1/8 of the mass of the original sample of a radioisotope remains unchanged after 4,800 years, the isotope could be. All right, so just in this previous example, I was able to show that after, let's see, 1 half-life you have a half remaining, a fourth half-life you have, or excuse me, a second half-life you have a fourth remaining, and after the third half-life you would expect an eighth to remain. So if you have an eighth of this sample remaining, it's probably been through 3 half-lives. But I'll just work through it forwards to backwards just to make sure you understand. So first half-life, you have a half remaining. Second half-life, expect a fourth. Third half-life, expect an eighth. So I know it's been going through its third half-life. Now also, it looks like it took 4,800 years to go through 3 half-lives. So if I want to know how much 1 half-life is, I'm going to do 4,800 years divided by 3 half-lives. And I'm thinking that's going to be really close to 1,600 years. Now they want to know which of these isotopes could it even be. And of the isotopes that are listed, the one that is really close to having a half-life of 1,600 years is radium-226. Now, to be clear, its half-life is, I believe, 1,599 years. But the reference table that you're using is a reference table from 2011, and this question could very well have been written before 2011. So if you ever see a slight misalignment between like an answer that you got and what the reference table said, like 1,600 versus 1,599, just I would say chalk it up to a difference between the year the question was written and the year the reference table was written. All right, so I have a little bit more half-life practice here, and I'm going to actually ask you guys to copy these down, and we can work on them during the pair-up section of tomorrow's class. And if absolutely necessary, we can go over them together as well. So please write down these questions. I think you'll find that they will correspond very nicely to the questions from the previous slide. And then here is a standard pair-up. So basically, if you're a pair-up, you should have 6 questions written. And also, don't neglect to write the summary. And here's the summary. So write those down, and we'll do all of this tomorrow. Have a wonderful evening.